أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله. هذه الآن presentation عن sizing gas to gas compact heat exchanger. Actually this is a part of the course which is MEP460 Heat Exchanger Design, which is offered in Mechanical Engineering Department, King Abdulaziz University. We are going to give a solved example on how to size gas to gas compact heat exchangers. The contents of this presentation will be: first, we are going to give idea about the problem statement, the input data and required output data. Then we'll go to summary of the input data in tabulated form. Then we need since we are going to need some properties, or we are going to list some of the physical property for the two fluids and in the two sides of the heat exchangers. Surface data, which is very important in order to solve the problem, is going to be taken from case in London, and actually is going to be taken from EASE program. Additional surface calculation has to be made before we go to the actual calculation. Then we go to the sizing calculation. In number 7 we give some conclusions about the whole sizing and solved example. List of references will be given in number 8, and then in number 9 we are going to give the same example actually solved in Arabic book, which is heat exchanger design. The problem statement is basically we are looking for how to size a compact heat exchangers, how to find the dimensions L1, L2, L3 of a heat exchanger. We are considering gas to gas compact heat exchanger, and the input data for this kind of example are as follows. The fluid for both the hot side and cold side is air. The surface for the hot side is a louvered fin with the number 3 by 8-11.1, and for side 2 it is a strip fin with a designation number 1/8-15.61. The inlet temperature for the hot side is 400, and for the cold side is 330 degrees C. The outlet temperature for the hot side is 86.2, and the outlet temperature for the cold side is 260.7 degrees C. The mass flow rate is 2.796 for the hot fluid, and the mass flow rate for the cold fluid is 3.861. The inlet pressure is 150 for the hot side and 120 for the cold side. The pressure max, allowable pressure max for the hot side is 7.156 kilopascal, and the allowable pressure drop for the cold side is 12.446 kilopascal. The heat capacity rate, which is the multiplication of the mass flow rate times the CP, the specific heat, is 2.884 for the hot side and 3.923 for the cold side. The plate thickness is 0.36 10 to the power minus 3 meter. Here in this diagram we show the red arrows for the side 1, which is the hot side, and also we see also the blue arrows for the cold side, which is side 2. The dimensions here is, as we said, for the hot side the frontal area is L1 times L2, and the frontal area for side 2 is L3 times L1. That's L1, then we call it the common edge, because it is the common edge for both side 1 and side 2. Other dimension which is very important is the spacing between the plates for side 1 and side 2. B1 here is the plate spacing for side 1, and B2 is the spacing between the plates for side 2. Also another important parameter is the thickness of the plate, which is A, which is given here as 0.35 millimeter. This is the input data. This is just a figure to show the geometry of the gas-to-gas compact heat exchanger, and the required actually is to find L1, L2, L3, so that this heat exchanger can fulfill the rate for this mass flow rate going to this temperature and this mass flow rate going through these temperatures, and the pressure drop for the hot side is this value and the for cold side is this value. So as if the statement of the problem is find L1, L2, L3 that satisfy the requirement of the problem. As we said before, the hot side is using louvered fin, and the cold side using a strip fin. So here in this diagram we show different types of fins that is used in gas-to-gas compact heat exchangers, but now we are for side 1 we are using this type of fins, which is louvered fin, and for side 2 we are using this one, which is as you see D, which is of strip fin. So this is for the hot side and this is for the cold side, just to know the geometry of the two sides. We summarize the input data in tabulated form so it will be easy for us to proceed. The gas is air for side 1 and louvered fin, the mass flow rate, inlet temperature, inlet pressure, outlet temperature, and the heat capacity rate. The same thing also for the strip fin, which is the cold side. We are giving also the same information. Of course, we need the thermophysical properties like the density, the specific heat, the viscosity, thermal conductivity, and Prandtl number. For the hot side, we are assuming an average temperatures of 240 degrees C, and we found from Encropera, which is a fundamental book of heat transfer, very well known. We took the data for dry air from there, and we find these properties for the hot side, and these the property that we are going to use for the cold side. Also again the density, specific heat, viscosity, thermal conductivity, and Prandtl number at average temperature. Okay, now the data, the surface data is very important to solve either rating or sizing compact heat exchanger. If we go to the book of Case and London for the surface that we have, which is louvered fin 3 by 8 11.1, we get this figure, and we get also the information here, the geometrical data also needed for calculation. All the figures for different type of surfaces, you will find them similar to this figure. In the x-axis we have Reynolds number, and in the y-axis we have two figures or two lines. One of them is for friction coefficient, the upper line, and the one below is for Colbrand modulus. Once you know the Reynolds number, which is here written as 4 times RH, 4 times RH actually is not more than DH, the hydraulic diameter. So the hydraulic diameter times G divided by the viscosity will give you Reynolds number. Of course, G is just the G is equal to the density times the velocity. So Reynolds number actually is DH multiplied by G divided by the viscosity. Once you get the Reynolds number, you can go to this figure and find how much is the friction coefficient and how much is the Colbrand modulus. Now this data is taken from Case and London compact heat exchanger book, or you can find it also from other sources like, for example, EASE program, engineering equation solver. You can find all the data that is given in Case and London book. Colbrand modulus actually, we call it, we give it the symbol JH, is not more than Stanton number multiplied by Prandtl number 2/3. Stanton number actually is that Nusselt number divided by Reynolds multiplied by Prandtl. If you substitute with the Stanton number, you get the Colbrand modulus as the heat transfer coefficient divided by CP times G multiplied by Prandtl number 2/3. So if you know from this figure how much is JH Colbrand modulus, then you can multiply it by Cp, multiply by G, and you divide by Prandtl number 2/3, you get the heat transfer coefficient. For the pressure drop, we know the relations that says the pressure drop is due to friction is 4 times the friction coefficient. This is friction coefficient, coefficient, not friction factor, multiply by the ratio L over dH, multiply by the kinetic energy rho v squared divided by 2. If you multiply this equation by rho in the denominator and numerator, then you can get G squared divided by 2 rho instead of rho v squared over 2. The data here below the figure is geometrical data. We would like to focus on some of them. For example, the plate spacing is given here in inches and in meter. Also, the flow passage hydraulic diameter, which is 4H, is given here as 3.084 times 10 to the power minus 3 meter. The fin thickness is given as 0.152 10 to the power minus 3 meter. Also, the heat transfer area divided by the volume of the heat exchanger is given as 1,204 meters square by cubic meters. The fin area divided by the total area, we are going to give it a symbol omega, is 0.756. We need all these data in order to perform the sizing calculation. So this data now for louvered fin, which is size 1, and here for the strip fin, also from KS in London, we get the same thing but for different surface. Also Reynolds number in the x-axis, and you have two lines, one for the friction factor and the other one is for Colbrand modulus. And the same thing applied as we said before in order to get the heat transfer coefficient out to get the pressure drop. Notice that the information here for the strip fin is totally different. For example, beta is 1548 meters square by cubic meters, and the same thing also for other parameters. It is not same because this is totally different surface. We summarize the geometrical data in two tables. The upper table is for the hot side, which gives the plate spacing, omega, which is the fin area divided by the heat transfer area, beta, which is the how much is the heat transfer area divided by the volume of the heat exchanger between the plates, delta, which is the how much is the thickness of the fins, hydraulic diameter, and A, which is the thickness of the plate. This is for the hot side and this is for the cold side. So the parameters also taken from the table that we showed just a while ago, summarized here in order to use them later. We would like to relate the frontal area, free flow area, and the heat transfer area. There are three areas actually that we have to understand. The free flow area is the area, the cross-section area of the flow. This is, we call it AFF. FF means free flow area. The heat transfer area actually is the perimeter times the length. If we consider this geometry, this will give you the heat transfer area. So we know now the free flow area, which is how much is the cross-section area of the flow. By definition, the hydraulic diameter equals 4 multiplied by the cross-section area divided by the wetted perimeter. Here we multiply by L and divide by L. L is the length of the heat exchanger along that side, along the sides, for example, side 1 or side 2. Now P times L, as we said, is the heat transfer area. So actually the hydraulic diameter is equal to 4 times the free flow area multiplied by the length of the heat exchanger along the direction of the flow divided by the heat transfer area. This is equation number 1. AFF is the minimum flow area and A is the heat transfer area, which is equal to the perimeter times the length. Actually, from equation 1 you can write the free flow area. So the free flow area from this equation is no more than A times DH divided by 4 divided by L. We need this definition for the free flow area when we calculate what we call the sigma, which is the minimum flow area divided by the frontal area. What is the frontal area? The frontal area, we talked about it when we talk about the geometry, the first problem statement. So it is, for example, L1 times L3 or L1 times L2 for side 1, for example. By definition, sigma is the minimum flow area divided by the frontal area. So if sigma is, as we said, the minimum flow area divided by the frontal area, we can write it as if sigma for side 1, AFF1 divided by frontal area 1, multiply by both numerator and denominator by LB1. You get the volume here, and here you get A times DH1 divided by 4. You can relate the area, the heat transfer area for side 1 to beta, since beta equals to the heat transfer area for side 1, for example, divided by the volume between the plates. This means that A1 equal V, the volume between the plates for surface 1, multiply by beta. Then multiply by DH1 divided by 4, and then divide the whole thing by the volume. Actually, you can write the volume of the heat exchanger in terms of the number of plates and the thickness of each side, B1 and B2, and the thickness also of the plate itself. So L3 times L2 multiply by this parameter, which is L common, will give you the volume of the heat exchanger. And here we can write the volume between the plates for side 1, not the volume, the total volume of the heat exchanger, the volume between the plates for surface 1, which is L3 times B2 times B1 times NB. And the rest is the same, beta DH1 divided by 4. Now you can see that in the numerator and denominator, we have NB and NB here, but we have here NB plus 1 and NB plus 1. We are going to assume that NB was plus 1 is roughly equal NP. So we are going to take NB as a common factor, L3, L2, L3, L2 common factors here and here. So we lift up with sigma, which is equal to B1 times beta 1 times the hydraulic data 1 divided by 4 divided by B1 زائد B2 plus 2A. You do the same thing actually. I'm sorry, but it's obvious that sigma 2 is going to be the same expression, but substituting 1, 1, 1, but with 2 instead of 1. Alpha also is a very fundamental parameter in designing and rating gas-to-gas heat exchanger or compact heat exchanger in general. It is defined as the heat transfer area divided by the volume of the heat exchanger. So A1, the heat transfer area divided by the volume. The volume can be written as the frontal area divided by L3. And also we can write the frontal area in terms of free flow area, or I'm sorry, the area, the heat transfer area in terms of the free flow area. And after that we can get to this expression, which says 4 times sigma divided by the hydraulic diameter 1, since actually the free flow area divided by frontal area is sigma, and 4 divided by dh, 4 divided by dh. And then since we have found sigma from this expression, so we can substitute in alpha the value of sigma from this expression. So this expression actually is, we know now that this expression is okay for sigma, so we can take it and put it here in this expression. So we get here an expression for alpha, which is the heat transfer divided by the volume of the heat exchanger. The calculation actually proceeds. Now we found an expression for sigma in terms of these parameters. We can also find we express the values of each of these parameters. So we get sigma for side 1, this value, in terms of meter square by cubic meters, and do the same thing for sigma 2, which is the free flow area divided by the frontal area. So we have also get 0.4365 meter square by meter square for side 2. Also alpha 1 and alpha 2 we have to calculate it based on the expression, and we found that alpha 1 is 570.6 meter square divided by cubic meters, which is the heat transfer area divided by the volume of the heat exchanger. The same thing also for side 2. If you would like to find the ratio, the heat transfer area of side 2 divided by the heat transfer area of side 1, which is just alpha divided by alpha, alpha 2 divided by alpha 1. We found alpha 2 and we found alpha 1, so the heat transfer ratio, which is needed actually in calculation of the overall heat transfer coefficient, is going to be 1.286, the heat transfer area of side 2 divided by the heat transfer area of side 1. From the input data, actually we can calculate the heat rate of this heat exchanger, which is basically equals to the mass flow rate multiplied by the specific heat multiplied by the temperature difference for side 1, the inlet temperature minus the outlet temperature for the hot fluid. This will give you the heat rate, which is 905 kilowatt. And the maximum heat rate, actually it can be found from the well-known expression, which says that the Q max equal C min multiplied by delta T max. Delta T max is the difference between the two inlet temperature of the two streams. With this expression, with this substitution with the values, the inlet temperature 400 for the hot fluid and the inlet temperature for the cold fluid is 30. This will give 1068.6 kilowatt as the maximum rate for this heat exchanger. If you divide the Q divided by Q max, you get what we call the effectiveness of the heat exchanger, which is going to be 0.848 for this type of heat exchanger. The CR, what we call heat capacity rate ratio, is actually C min divided by C max. We know C min and we know C max, so if we divide these by if you divide C min by C max, you get 0.736. Now we know that from a basic heat exchanger that if you know the effectiveness and you know the CR, you can find the NTU. But for our case, since we have a cross-flow heat exchanger with both fluid and mixed, there is no direct relation that gives NTU as a function of CR and the effectiveness. We have to use the expression for the effectiveness as a function of CR and NTU and solve it to get NTU based on given value of the effectiveness and CR. The expression for the effectiveness of cross-flow unmixed and mixed heat exchanger is given by this equation. We are going to see the source of this equation in short time, but it's very clear that in the left-hand side we have the effectiveness and in the right side we have the NTU and CR. We would like to use this equation to find the NTU based on this value of CR and this value of the effectiveness using any kind of iteration technique, like for example MATLAB or Excel or for example Newton-Raphson method. If you do that, actually you end up with NTU based on these two values, you get 5.754. Just to remind ourselves, in the book of Encropera, there are two tables actually very fundamental for most of the types of heat exchangers, where in table 11.3 will give you the effectiveness as a function of NTU and CR for different types of heat exchangers. Our heat exchanger actually is cross-flow both and mixed, so you have this equation 11.32, which is exactly the equation that I showed you in the previous slide. There is another table which is 11.4 that gives NTU as a function of the effectiveness and CR. As you can see, for the cross-flow actually unmixed and mixed, there is nothing here. So all what we are saying is that you have to go to this equation and solve it to find NTU as a function of the effectiveness and CR. Now, if we neglect the conduction in the plates and we neglect also the fouling of this heat exchanger, then we can write the resistances, the thermal resistances, as in terms of overall heat transfer coefficient based on the heat transfer area 1 is as this is actually the resistance for side 1, and this is the convective resistance for side 2. You can multiply this equation by Cmin, so you will get Cmin divided by UA, which is actually 1 over NTU, because NTU is UA multiplied by A divided by C minimum, and you also multiply by Cmin here. We are going to assume that NTU1 and NTU expressions as follows. So in NTU1 actually is the heat transfer coefficient for side 1 multiplied by the area multiplied by overall surface efficiency divided by C1, and the same thing for NTU. So NTU1 and NTU actually are function of the heat transfer coefficient for that side, which is either side 1 or side 2. Now, assuming that this resistance of side 1 and the resistance of side 2, since they are both gases, so they are going to be of the same order. So as if we are saying that this one and this one almost the same. In that case, we can write actually 2 as for both of them divided by NTU1 C1 C minimum, and because this one is the same as this one, also it's going to be 2 divided by NTU2 C2 divided by C minimum. So if we know NTU that we found just a while ago, we can find NTU1 and NTU2. We did that, so NTU1 is going to be 11.51 based on NTU, actually the one that we found a while ago, and NTU is going to be 8.37, where the definition of NTU1 and NTU2 is given by these two equations. Approximate mass velocity can be found using this expression, and this expression is going to be, it will give you an approximate value for G1 and of course G2. Now we'd like to know how this expression came to, so we are going to now derive these two expressions, or one of these expressions, because it is very similar. This is for side 1 and this is for side 2. To find an initial guess for G1 and G2, we can use the since we know that the pressure drop due to the friction is given by this equation, or in terms of G is going to be this equation, then we can actually from equation 1 we can write G on the left hand side as equal this expression, and then after that actually we can use the definition of the hydraulic diameter, which is 4 times the free flow area divided by P, which actually turns out to be 4 times the free flow area multiplied by L divided by the heat transfer area, which is equation number 3. From this equation number 3 actually we can take dH by divided by L, because we need it here in the equation number 2 to be 4 multiplied by FF free flow area divided by the heat transfer area. So G in this case is going to be given by this expression. In equation number 5 we found the G value as a function of these parameters here up to raised to the power 1/2. We need also to get rid of the heat transfer area, the free flow area divided by the heat transfer area, on terms of other parameter that we can find an initial guess for G1. Equation number 6 actually equation number 5, I'm sorry, is written in general, and equation number 6 is written for the mass velocity for side 1. We need to get rid of, as we said, the heat transfer area. We use the definition of the number of transfer unit, which is given by this expression in equation number 7, from which we can write the area that is we need in equation 7 as a number of transfer unit 1 multiplied by m dot Cp for side 1 divided by the heat transfer area multiplied by the overall surface efficiency. Also we would like to express H1 in terms of the heat Colbrand modulus, we know that, as we explained before, there is a relation between the Colbrand modulus and the heat transfer coefficient. So actually you can write the heat transfer coefficient from equation 9 as JH multiplied by GCP Prandtl number to minus 2/3. So what we did actually is that we use equations 9 in equation 8 to get an expression for A1, so that we can use it in equation number 6. Now the heat transfer area is given by this expression, which include JH, G1 multiplied by C1, CP, specific heat 1 and Prandtl number, and also eta 01, the overall surface efficiency for side 1. And we are going to assume a constant value at the beginning, which is around 0.8 for this overall surface efficiency. Note that here m dot, when you have m dot here and CP, you have also CP here. Since we're going to substitute this A1 here in expression 6, we get equation, if you notice that we have a free flow area here, and we have m dot here. When you divide m dot by the free flow area, you get G. So G times CP is going to go with m dot divided by the free flow area multiplied by CP. So these two terms will go with these two terms along with the the free flow area. I'm sorry. Then you can equation number 6 is going to get to this simplified form, which actually very important. We have the ratio of the heat transfer coefficient divided by the friction, which is sometimes they call it the figure of merit. How much is heat transfer how much is friction is transformed into heat transfer, and the other parameters that we see here in front of us. You can do the same thing for G2 by expressing the same by using the same expression with 2, 2, 2 instead of 1, 1, 1. Now we are going to use this equation for the initial estimation of G1 and G2, assuming that this ratio is going to be 0.3, and we are going to see the source of that assumption, and we are going to assume that the overall surface efficiency is going to be approximately 0.8. Other parameters are well known. For example, NTU1, we found it, since we know NTU for the whole heat exchanger, we can find also NTU1 and NTU2 as previously was done. If you go to, if you use the expression, the initial guess for G1, which for side 1, and substitute the values that we know, notice that we are assuming that JH divided by the friction coefficient to be 0.3, and also we are assuming that the overall surface efficiency for side 1 and side 2 actually is going to be 0.8, and put the pressure drop, which is the allowable pressure drop for side 1 and side 2, as 7156 Pascal here for side 1 and 12,446 for side 2. If you substitute with these values in G1, you get an initial value for G1, which is going to be 19.7 kilogram per meter square second, and the same thing for G2. These two values are initial guess, so we are going to use these values in order to get Reynolds number, the heat transfer coefficient for both sides, in addition to other parameters, so in order to get the U value for the heat exchanger. As we said before, in order to go and proceed, the assumption that we did is that the overall surface efficiency, and in addition to that also we assumed that this ratio, the heat transfer Colbrand modulus divided by the friction coefficient to be 0.3. Here, this from Case and London shows the reason why we are assuming JH divided by the friction coefficient to be 0.3. This figure from the book of Case and London shows the variation of this parameter, which is heat transfer coefficient divided by the friction coefficient as a function of Reynolds number. So in x-axis you have Reynolds number, and y-axis you have this ratio. For different surfaces, for example, and actually if you know the surface, you can draw this figure for the surface that you know. But since we are going just to assume approximate value, we can find that JH divided by friction coefficient is around from 0.1 or 0.2 to 0.3. maybe more, maybe less. So the value is ranging from 0.1 to 0.3, maybe more, to 0.5 or 0.4. So he assumed actually in case in London, the value is to be assumed to be 0.3 as initial guess to find G1 and G2. For more accurate value, you can do the following. You know the surface, so you go to case in London and draw the ratio of JH divided by FC for different values of Reynolds number, and then you pick some kind of an average value for Reynolds number and you get this ratio. Of course, in our assumption, we are assuming that this ratio is going to be 0.3 for both G1 and G2 estimation. This is, as we said before, the ratio of Kalman modulus divided by the friction coefficient. Now, we found the value for G1 and G2. So now we can proceed find Reynolds number for side 1 and Reynolds number for side 2. And we go to the chart, the case in London for two surfaces that we selected, the louvered fin and the strip fin, and find out how much is the J value and the friction coefficient. Of course, once you know Reynolds number and know the surface, you can find these two values. For our surface, the first one is, as we said, louvered fin. So you know Reynolds number is found. So actually you can get these two values, this value, the friction coefficient, and this value which is Kalman modulus. We found them to be these two values for the surface 1. And for surface 2, actually, since we have what we call a strip fin, also since we calculated the Reynolds number, you can go to these two curves and find out the JH1, the Kalman modulus number for side 2, and also the friction coefficient. Of course, once you do that, you can actually use JH1 to find the heat transfer coefficient for side 1, which is going to be 236.1 watt per meter square Kelvin. You do the same thing also for side 2. Since you know that the Kalman modulus is 0.0095, you can get also the heat transfer coefficient for side 2, which is going to be watt per meter square Kelvin. Now, since we know the heat transfer coefficient side 1 and heat transfer coefficient side 2, also we can calculate the overall heat transfer. But before that, we have to calculate the fin efficiency and the overall surface efficiency. For these two surfaces, we are going to assume that the length of the fin is going to be the spacing divided by 2 for either surface 1 and surface 2. So we have the length of the fin is going to be this value, and the length of the fin for side 2 is going to be this values in meters. The fin thickness, according to the data of the surface, for surface 1 is going to be 1.52 millimeter, and for surface 2 is going to be 0.102 millimeter. We are assuming a straight fixed cross-section fin, so we can use the expression that all we know, that the efficiency of the fin is going to be tanh M1 L1 divided by M1L, the length of the fin. So M1 is going to be 2 times H1 divided by the thermal conductivity of the fin, divided also by the thickness of the fin, which is for side 1 is going to be this value, and then you multiply this value by the length of the fin, and you take the tanh and you divide it by the value of M1L1, so you get the fin efficiency to be 0.907, from which you can also calculate the overall surface efficiency, which is given by this expression 1 minus omega. Omega, we said that it is the ratio of the fin area divided by the heat transfer area, which is a given parameter from Case and London properties or surface properties for that particular surface, which is in our case is louvered fin, multiply by 1 minus the eta f, which is we found the fin efficiency. So you substitute with these values, you get the overall surface efficiency for side 1. You do the same thing for fin 2, exactly the same procedure to find the fin efficiency for side 2, and from which also you can also find the overall surface efficiency, which is 0.824. So we found the fin efficiency to be 0.907 for surface 1, and the overall surface efficiency to be 0.92. And actually the same thing, we found that the fin efficiency for side 2 is this value, and the overall surface efficiency is this value for side 2. Now you calculate the free flow area since we know that by definition G actually is the mass flow rate divided by the free flow area, so actually you can find the free flow area. We divide the flow rate of the side 1 divided by G1 that we estimated. So this is the frontal area, the free flow area. It's going to be 0.1417. Since we know that there is this is the same thing for side 2, I'm sorry. So this is the free flow area for side 1 and free flow area for side 2. But we know sigma 1 and sigma 2. Sigma 1 and sigma 2 are the free flow area divided by the frontal area. So we can find, since we know now sigma and we know also the free flow area for both sides, we can find the frontal area for side 1 and frontal area for side 2. So this is the frontal area for side 1 and this is the frontal area for side 2. Once we know this one also, we can, of course, we know the efficiencies. So the overall heat transfer coefficient is given by this expression, assuming that we have only two resistances, which are the resistance in the convective resistance for side 1 and convective resistance for side 2. So we substitute with the values. Of course, we calculated H1 and H2, the heat transfer coefficient for side 1 and side 2. We also calculated eta 01 and eta 02, which are the overall surface efficiency for side 1 and side 2. And also we know the area ratio A2 and A1 with this value. So when you substitute in this, you get the value of U1, which is the overall heat transfer coefficient, 141 watt per meter square Kelvin. We know that the number of transfer unit is given by U1 multiplied by A1 divided by C minimum. We already found U1. We know NTU. We know C minimum. So actually you can find the heat transfer area. So the heat transfer area for side 1 is going to be 117.9 square meters. And do the same thing, since we know that the heat transfer area of side 2 divided by the heat transfer of area 1, which is alpha 2 by alpha 1, is going to be 1.286. So actually you can find also the heat transfer area for side 2. So now we have calculated the heat transfer coefficient, the overall heat transfer coefficient, the fin efficiency for side 1 and side 2, the overall heat transfer coefficient U, the heat transfer area for side 1, the heat transfer area for side 2. Now after that, what we can do is that actually, since we know since actually we know the heat transfer, the frontal area for side 1 and the frontal area for side 2, we can find also from the expression of alpha that we calculated for side 1, that there is a relation between alpha actually is the heat transfer area divided by the volume. So you can calculate the volume, since the heat transfer area for side 1 has been calculated, and alpha 1 and alpha 2 has been calculated, which are, as we said, the heat transfer area divided by the volume. So you can get the volume. Once you get the volume and you know the frontal area for side 1 and side 2, you divide the volume by the frontal area for side 1, you get the LB1, which is the length of the heat exchanger along the side 1, which is going to be 0.6342 meters. You do the same thing for side 2, you divide the volume of the heat exchanger. This should be the volume of the heat exchanger, not V1 actually, since we are talking about only the volume of the heat exchanger, not volume 1. Volume of the heat exchanger is given by this value. You divide this volume by the frontal area, you get the length of the heat exchanger along side 1, and the same thing the length of the heat exchanger along side 2. And then here actually is showing LB1 and LB2 and L3, the three dimensions of the compact heat exchanger. This is the frontal area, and this is LB1, which is the length of the heat exchanger along the direction of side 1. And here this is the frontal area for side 2, and this is actually LB2, which is the length of the heat exchanger along LB2. We found the volume of the heat exchanger is given by this value. If you divided the volume of the heat exchanger by the frontal area for side 1, you get LB1. And if you divide the volume of the heat exchanger by frontal area 2, you get LB2. Since the volume is known, which is 0.21, if you divide the volume of the heat exchanger by LB1, LB2, you get L3, which is the common factor or the common edge of the heat exchanger, which is going to be 0.463. So to summarize, we went through a lengthy procedure to calculate the heat transfer coefficient for each side, the overall surface efficiency for each side, the overall heat transfer coefficient U1, and then the frontal area for 1 and frontal area for 2, and then the length of the heat exchanger, all of them, I mean the dimension of the heat exchanger, LB1, LB2 and L3. Now we would like to know whether these values that we found for the dimension of heat exchanger satisfying the pressure drop, the maximum pressure drop for side 1 and side 2. So we have to go to calculate the actual pressure drop for side 1 and side 2 using all the data that we have calculated. So here we can see that the pressure drop actual for side 1 is going to be 4 times the friction coefficient for side 1 multiplied by the ratio, the length of the heat exchanger along side 1 divided by the hydraulic diameter of side 1 multiplied by g squared divided by 2 rho 1, you get 5799.2 Pascal. You repeat the calculation using the expressions that we found, the data that we found for the volume of the heat exchanger, to find also the pressure drop for side 2, and it's going to be 20 kilopascal, 0.302 Pascal. If you compare these two values with the delta P maximum that we have to fulfill for this heat exchanger, you find that they are different. After finding the pressure drop for side 1 and side 2, we have to do to compare the pressure drop actually with the maximum pressure allowable for side 1 and side 2. We have found the pressure drop actually how much, and we know how much is the pressure allowable pressure for side 1. From this calculated values, we found out that the difference between the actual pressure and pressure drop and the pressure drop allowable is minus 19 for side 1, and for side 2 is going to be 63, which is much higher than the actual pressure drop allowable for side 2. So for this case now we have to repeat the calculation again until we get to the conversion criteria. The conversion criteria, actually we set how much is the allowable delta P1 and how much is the allowable delta P2, at which we stop conversion, and we say that conversion has been achieved. In order to calculate new estimate for G1 and G2, we use the general equation that we know about how to calculate delta B, but we convert it into G. So we put G in the left hand side and all the parameters in the right hand side. Of course, the density, the hydraulic diameter are known, the pressure maximum is also known, but here we are going to substitute with the friction coefficient and the length of the heat exchanger alongside 1 with whatever values we found. We do the same thing for G2. Also we use the pressure drop, how much is the allowable pressure drop, and the calculated value of the friction coefficient and the length of the heat exchanger along side 2, and we also find how much is G1 and G2. For for our example, when we substitute with these values, we find G1 21.92, which is totally different from the initial value of G1, and G2 23.55, the unit is kilogram meter square also. Now since we have these two values, we have to go through the process again and calculate how much is the Reynolds number, the heat transfer coefficient, the overall heat transfer coefficient, fin efficiency, overall surface efficiency, and how much is the frontal area for each side, the volume of the heat exchanger, and the length of the heat exchanger, and finally how much is the actual pressure drop for side 1 and side 2. Then we have to compare the difference between the actual pressure drop and the maximum pressure drop for each side, and then we have to either finish or find the solution, or we have to go to take another iteration for finding new values for G1 and G2. Therefore, actually, since the process is going to be lengthy to go through the calculation of the heat transfer coefficient, overall heat transfer coefficient, and fin efficiency, and so forth, we have to use some kind of a program to do these calculations. In our example, we have used MATLAB program to do the calculations and find out the design values for the heat exchanger dimensions. What we did actually, we put this thing into a MATLAB program and use the ifsolve for the iteration to find out actually the result, the convergence after several iteration, and this table actually summarizes the after few iterations some of the parameter that ended with this MATLAB program. So the pressure drop for side 2 is this value, and the pressure drop for side 1, which are very close to the values as we are going to see later. And the length of the heat exchanger actually as you can see here 0.508 for L3, and this value for LB1 and LB2. This is the overall heat transfer coefficient. This is the heat transfer coefficient for side 1 and side 2, and this is G2 and G1 with the dimensions written here, and the dimensions also in Arabic terms. If you can compare these values, this is for this iteration with the value that is given in the statement of the problem. So we know that delta B1 maximum is 7156. The value here found is 7433, a little bit more, but actually it's up to the designer to allow how much is the pressure drop between the two, between the actual value and the maximum value at which the convergence will end. And the same thing for side 2, the pressure drop is 12,446 compared to 12,102. Of course, this one is higher than this one, but actually you can change the tolerance between the two, and then you can proceed your calculation to end up to whatever you like to do. One thing you have to, I would like to remind our viewer is that this problem actually is written, is available in the book, the Arabic book of a heat exchanger design, for both rating and sizing of the same problem. So we have two problems, 9.3 and 9.4 in the Arabic book, that one of them is rating and the other one is sizing. We would like also to summarize the process of sizing gas and gas-to-gas heat exchanger. This actually, since we know that the process is very lengthy, this flow chart actually describes the whole process together in one chart. We start with, of course, the input data that is given about the heat exchanger, including the inlet temperatures, the two surfaces, the allowable pressures for side 1 and side 2. We also know, we would like also to be able to find the properties, the thermophysical properties like the CP, the viscosity, thermal conductivity, and Prandtl number for the fluids that are used in this heat exchanger. So this has to be provided as a subroutine, for example. We can calculate the Q and Q max, as we said just a while ago. The Q is known, Q max is known. You can find also the heat exchanger effectiveness and CR. Then you go to another subroutine to find the NTU based on these two values of the effectiveness and CR, from which you can find actually in this step the NTU 1 and NTU 2 for side 1 and side 2. Now we start the process here by assuming initial guess for G1 and G2 based on certain assumptions for the overall surface efficiency for side 1 and side 2, and the ratio of heat transfer by the friction for side 1 also and side 2. Once G1 and G2 are known, then we go to the next step where you find the Reynolds number, and from Reynolds number and the data that we have, geometrical data and the heat transfer and friction coefficient data, we can, from using Reynolds number 1 and Reynolds number 2, we can find actually the friction and the heat transfer coefficient in terms of Colburn modulus, which are JH1 and JH2. Then actually you can calculate the heat transfer coefficient for side 1 and side 2 based on these values found for JH1 and JH2. Then you can calculate actually the fin efficiency and the fin overall surface efficiency for side 1 and side 2. This will help in finding the overall heat transfer coefficient, since we are assuming that only we have two resistances. Then we can find the U value. Of course, you can consider other resistances if you want to, if the data is available for that. If you end up with in this step finding the overall heat transfer coefficient U, then actually you can calculate the heat transfer area and the volume of the heat exchanger. The heat transfer area actually is known since the NTU is known and U value is known. Since NTU actually equals U multiplied by the area divided by C minimum. C minimum is known, NTU is known, U is known, so you can get the area. from the surface data, we know alpha 1 and alpha 2. We have calculated alpha 1 and alpha 2. Alpha is basically the heat transfer area divided by the volume of the heat exchanger. We calculated the area here in this step, so we can calculate actually the volume of the heat exchanger. Since also sigma 1 and sigma 2, which are defined as the free flow area divided by the frontal area, actually we can find the free flow area since we know G and we know the mass flow rate. So the free flow area for 1 and 2 are known, and then we use sigma 1 and sigma 2 to find the frontal area 1 and frontal area 2. Since the volume of the heat exchanger has been calculated, frontal area 1, frontal area 2 has been calculated, then we go and calculate the dimension of the heat exchanger, which is LB1, which is the length of the heat exchanger along path 1, and the heat exchanger along path 2, LB2, and L3, which is the third dimension of the heat exchanger. Then we have to go and calculate the pressure drop, actually how much, delta T P1 actual and delta B2 actual how much, and compare this actually with delta B allowable for side 1 and side 2, and if we find it is outside our criteria, then we have go and modify G1 and G2. So we have to calculate new values for G1 and G2, and when we have, and then after that we have to go and proceed and list until we get to another value of delta B actual 1 and delta B actual 2. When you find that the delta P 1 actual and delta B2 actual are within your tolerance, the designer tolerance, then we stop the process. So actually G1 and G2, once you know them, you have to go to a lengthy process in order to find the dimension of the heat exchanger and find how much is the delta P1 and delta P2 actually how much. So we would like to summarize the procedure of sizing or designing a gas-to-gas heat exchanger. It is obvious that this procedure is very lengthy actually, and you need a lot of parameters to be calculated. It is highly recommended to use software to speed up the process and achieve convergence. In this example, the following are assumed. Actually, we have to emphasize that we are assuming certain things that it has to be said at the beginning of the sizing or solution of the problem. We are neglecting the conductive resistance in the plate. We are also assuming the pressure drop is only due to friction. So we are not considering, for example, the inlet pressure drop or the exit pressure drop or the acceleration and deceleration pressure drop. This is just focusing only on friction pressure drop in order to understand the whole procedure. Of course, there is no fouling resistance. Also, we assume no fouling. Of course, the surface data for the friction coefficient, the J factor, actually is taken from EASE program, which is this is the site for the EASE program, if somebody is interested, because actually EASE program has tabulated all the values of Case and London, or most of them, Case and London book of the compact heat exchanger, so that for example, if you have a surface and you know the designation of the surface, with given any Reynolds number, actually you can find JH and the friction coefficient immediately. Digitally, you can find the value of the friction coefficient and the Culpeper modulus once you have Reynolds number for any given surface in the book of Case and London. In addition to all the parameters, like for example alpha and beta and hydraulic diameter and omega, which is the fin area divided by heat transfer area, are also, all of them are tabulated in EASE so that you can use it. What we did in MATLAB program, actually, we took the tabulated data from EASE and inserted into MATLAB, so that MATLAB now have all the data, tabulated data of all the surfaces. So once you give the program the designation for that surface and the Reynolds number, you get all the properties that you need, which are needed in sizing compact heat exchanger. The sizing of the sizing calculation actually for the first trial was done manually by hand, but then after that all the calculation has been done by MATLAB. Of course, here we are emphasizing the fact that in order to do sizing of compact heat exchanger, you need the data, the heat transfer data, which is actually J, the Culpeper modulus and the friction coefficient in terms of Reynolds number to be tabulated or in a digital form so that you can easily access them. These are some of the references that are very important or needed to understand rating and sizing of compact heat exchangers. Of course, Case and London is a very important one because it has several data and the data information are there. So this is reference number 1. Reference number 2 actually is a very good chapter or paper about the compact heat exchanger design from the book of fundamental thermal compact heat exchanger procedure in a book called Thermal Hydraulic Fundamental and Design in 1981. This is very important actually reference that summarizes a lot of things about sizing and rating of compact heat exchanger. A relatively recent book, Fundamental of Heat Exchanger Design by Shah and others, also has very good information about compact heat exchangers. Kakash and others, the heat exchanger selection and rating, thermal design. It has also a complete chapter about compact heat exchanger, but no more detail about designing compact heat exchanger, only rating compact heat exchangers. Ozisk has a good, at the end of the book, some examples about compact heat exchangers. This reference, Hodge, analysis and design of energy system, it has also some few pages about liquid to gas compact heat exchangers. We need this reference actually for the properties and the heat transfer coefficient for some geometries. So Encropera book is a very well-known book about fundamental of heat and mass transfer. And alhamdulillah rabbil alameen, wassalatu wassalam ala sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. As I said before, the Arabic book المبادلات الحرارية أداءها وتصميم حراريا. This is a recent book in 2023 about heat exchanger design. With it we have different type of heat exchanger like compact heat exchangers, gasket heat exchanger, cooling towers, chill and tube heat exchangers and others actually, and it has also in it several appendices for sizing and rating heat exchangers. This book actually is from King Abdulaziz University Press, and it can be found from this center, and the book is titled, as we said, is Heat Exchanger Design. In that book we have several examples for compact heat exchanger. Two very important examples in Arabic is 9.4 and 9.3. 9.3 actually, for this chapter, which is chapter 9, for the compact heat exchanger, we have several solved example. But for this particular case, we have for designing and rating gas-to-gas heat exchanger, since it is a very lengthy one, we have two examples, 9.3 and 9.4. 9.3 actually in that book is solving a rating gas-to-gas compact heat exchanger, and 9.4 is reversing the problem in 9.3, so make it as a design, a sizing, a designing problem instead of rating. And if somebody is interested, this is page number 1 or 351, page 351 in chapter 9, and this is the statement of the problem, which is exactly the same that we did in English, and the pressure drop that is allowable in 1 and 2, and also the inlet data for side 1 and side 2, the heat transfer area, exactly the same thing that we did in English. That is the whole procedure of finding the size or sizing of the heat exchanger. So this is 352, which is page 2, and this is page 3 finding the heat transfer coefficient and the initial value for G1 and initial value for G2 as we explained actually in English. Sigma 1, sigma 2, alpha 1, alpha 2, the frontal area, the overall surface, the fin efficiency and the overall surface efficiency, the overall heat transfer area, overall heat transfer coefficient, and the area, the frontal area, the length inside one and the length of the heat exchanger, LB1, LB2, L3, and also the calculated pressure drop, exactly the same as we did. And also we compare the pressure drop actual with the pressure drop allowable for 1 and 2, and then we proceed with another iteration for G1 and G2. So it is exactly the same but written in Arabic. And also we have as we said before, we have some kind of restriction because we ignore the conduction in the plate and ignore also the fouling and also pressure only due to friction. ولله الحمد والمنة.